Hi students, under the subject Algebra and Number Theory, we are under Unit 2, Finite Fields and Polynomials. So in that, the topic for discussion is Irreducible and Reducible Polynomials Part 2. This is lecture number 6. So I hope everyone followed up till lecture number 5. So in my previous part 1, I had explained what is a irreducible polynomial and what is a reducible polynomial. So a small brush up, a polynomial which can be written as a product of two polynomials, then of lower powers, then it can be called as a reducible polynomial. If not, it is termed as irreducible polynomials. So there we had seen how to evaluate an irreducible polynomials over the modulo arithmetic, modulo division. So let's get into the PPT. Now let's have the outline here. Outline here, I'm going to just mention few problems under irreducible and reducible polynomials, which will help you to master out the procedure. And next, I'll just give you a small theorem which is called as a reducibility test. So now first problem. So to start up with, I'm starting with a simple problem. I'm taking a polynomial of third degree. F of x is equal to x cube plus x plus 1, which belongs to z2 of x is irreducible. They are asking you whether this is irreducible. Is this polynomial which belongs to z2 of x is irreducible? So how will I handle this problem? It's a very simple problem. So I know what is z2. Z2 is a set which containing two elements, right? It's going to be a field. So the first element is 0 and second element is 1, right? So two elements should be there. So what will I do? How will I find irreducibility? How will I check irreducibility? Roots or whatever it is. After finding out that z, I'll go and substitute this every value of that in that particular polynomial and see what is the remainder. If the remainder is 0, then I can call it as a root, and then I can extend that idea to a factor and even for a reducible polynomial. So first I will substitute 0. So if I substitute 0, this will be 0, 0, and the answer I'm getting is 1. So this 1 is not equal to 0, right? This 1 is less than 2, so it cannot be divided. Just put not equal to 0. And second number is 1. So substituting 1 over here, I get 1 plus 1 plus 1. So the answer is 3. So 3 is greater than this 2. So I can divide this 2 over 2. So the congruence modulo here, the remainder will be 1, which is not equal to 0. So in both cases, for both the elements, okay, I'm getting the answer as your remainder is non-zero. So what my conclusion will be? Therefore 0 and 1 are not roots of f of x. So then f of x is irreducible over z2. Able to follow? So this type of questions you should be able to handle. So first, whatever it is, whenever you see a modular arithmetic, that you declare the set and start substituting those values inside the f of x and see whether the remainder is 0. If the remainder is 0, I can call that as a root. I can make it as a factor. I can even extend that to a reducible or reducible polynomial. So we move on to the next problem. So problem number 2. Now let f of x is equal to x cube plus x square plus x plus 1, which belongs to z2 of x again. Is it reducible or reducible? They are asking us to check and examine. If reducible, find the other factors. Is that clear? So let's check out. So f of x is equal to x cube plus x square plus x plus 1, which belongs to z2 of x. As I mentioned earlier, z2 is a set which contains two elements, 0 and 1. So what do? I substitute 0 first. If I'm going to substitute 0 first, what will I get? 0, 0, 0, 1, which is not equal to 0. So therefore 0 is not a root. Are you able to understand? 0 is not a root in Z2. Now I'll substitute 1. If I substitute 1, my answer is 1 plus 1 plus 1 plus 1 again. So my answer is 4. So is 4 divisible by 2? Yes, it is. So if I'm going to divide this 4 upon 2, my remainder is 2. So I'll be writing 2, 0 of mod 2. So therefore I can declare saying that 1 is a root, or I can also say x minus 1 is a factor. Is that clear? So Now out of out of two elements, I could see that one is not satisfying, one is not a root, and one is it is a root. So from that, which is a root, I'm going to derive the factor. Now since they're asking if irreducible, find the other factors they're asking. So you've got to divide that particular polynomial by the factor. That is, factor in the sense can be divided, right? So that number you can put it as g of x here, divisor. So dividing these two, you know how to divide this. This was earlier mentioned, discussed in your lecture number 3 and lecture number 4 about what? Division algorithm. So x cube upon x, you get x square, put x square on the top, multiply it again, change the sign, and keep an eye on the coefficient of the variables. If the coefficient of the variables are greater than 2 of that particular mod, you got to write the remainder. If the remainder is 0, that particular term itself will get vanished. So here I am getting x cube minus x square. Change the sign, cancel it out. Change the sign, cancel it out. So bring down this x and plus 1. Again you are going to divide this x upon x. Your answer will be 1. So put that 1 on the numerator, on the quotient. So take this 1 and multiply. It's going to be x minus 1, which is again changing the sign, you get it as 0. So therefore it's perfectly factorizing it. So this f of x can be written as x minus 1 into this. So how did I get this? This is by division algorithm. Division algorithm says that the dividend, the term, the polynomial which is divided can be written as a product of quotient into the divisor plus the remainder. Since the remainder is 0, we can just omit it. I would understand this particular problem, right? So first, this is a new concept. So first, what do you do? Out of the whatever may be the elements, try to find out the root of that particular polynomial and get the factors out of it. If they are asking you to find the other factors, you got to use that factor as an element and just divide it, and you get the other factors, and you can write as a product of the other factors. So problem number 3. Find two non-zero polynomials f of x and g of x in Z7 of x such that f of x into g of x is not equal to 0. So f of x into g of x is nothing but it is irreducible. So here when you multiply these two, you should not get it as 0. But both should be non-zero polynomials in Z7. So what is Z7? 0, 1, 2, 3, 4, 5 and 6. So what is f of x and g of x? Now you might ask me, there is a big question arising here for the students. How can I write this as 2x square plus 4x plus 1, and how could I write it as 6x cube? Will it satisfy? Okay, my only concern here is it is absolutely your wish. Your wish saying that you can choose randomly any two polynomials of your kind, right? So that it belongs to Z7, right? These two polynomials should belong to Z7. So always remember, Z7 means what should I do? I should choose numbers less than 7. If I'm going to choose greater than 7, I have to divide, modulo, etc. It is again going to be a tedious process. So what you're going to do, choose a number where the coefficients are less than that particular mod, where things will be easy for you, right? So now what do you do? Why have I chosen x square on one of my polynomial equation and the other as x cube? See, just observe. If I'm going to multiply these two, what will be the coefficient? If I'm going to multiply, I'll be getting, see, they are multiplied here, 2x square plus 4x plus 1 into 6x cube. If I'm going to multiply these two, I'll be landing up with 12x cube plus 24x power 4 plus 6x cube. So now x cube, I cannot separate x cube, right? So it's going to be an odd power. And also 12. 12 if I'm going to divide by 7. Yes, it is not perfectly divisible. In fact, it is one time and the remainder is 5. So I write the remainder here. What is 24? 24 is 21 and remainder is 3. 6 is short of 7. So I'm just writing it as 6x cube. So this is what the answer is. When I multiply these two polynomials, I'm getting a polynomial where the coefficients of the variables are not equal to 0, because we have chosen in such a way. So it is absolutely your thinking coming into, your creativity coming into framing the polynomial equations. So see to that when you are multiplying or when you are dividing or something with a modulo, definitely it should be non-zero. Then only it can be satisfying this particular condition. Therefore, it's not equal to 0. So the next problem will be the contrast of this. You've got to find f of x and g of x, which is equal to 0. So let's see how to do it. So problem number 4, as I told you, find two non-zero polynomials f of x and g of x. This is g of x in z12 of x such that f of x, g of x is equal to 0. So solution, we know z12. So what is z12? A set containing 0 to 11 elements. So totally you will be having 12 elements starting from 0 ending at 11. So what is your f of x and g of x? We got to consider this in your z12 of x. So always choose a number which is less than that 12, as I told you. You can go with 8 also. They have chosen 8 here. And they have chosen 3, 4. Okay. We know that there are non-zero polynomials. Try to take up anything. No restrictions in the past. You just multiply them. And the answer will be 3x square into 4x plus 8. Which is equal to 3x square into 4x will give you 12x cube plus 3x square into 8 will give you 24x square. So 12 is perfectly divisible by the modulo 12. So what is the remainder? 0. So 24 is also perfectly divisible by 12. So the remainder is 0. So both the cases you are getting the remainder as 0. So totally 0 plus 0 is going to be 0. So hence f of x and g of x are non-zero polynomials, whereas it is a zero polynomial in z12 of x. Able to understand? So the contrast of the previous problem, there we had chosen any type of polynomials you can choose such that the product, okay, the product exists, and under the particular modulo, if I wanted to be 0, if you want to get an answer as 0, you choose accordingly the perfect factors which can be divisible by 2. If it is not equal to 0, choose a number which is not divisible by 10. So likewise, you can continue with this particular problem. So the end of this particular problem number 4. So now next we'll just discuss a theorem called as reducibility test. Okay. So this also comes under irreducible and reducible polynomial topic. So let f be a field and f of x belongs to capital F of x. Then there are two conditions that get satisfied. F of x is of degree 1, then f of x is irreducible. So whenever I say a polynomial is of degree 1, it is irreducible. If f of x is of degree 2 or 3, then f of x is irreducible if and only if f of x has a root in capital F. So we have already seen this in the problem. That's why I have given the problems before, so that you can understand the concept easily. Then we are moving on to the theorems. So now, there are two conditions to be proved here. So f of x is of degree 1. So when you have a degree 1 polynomial, definitely you can say it is irreducible. And when you have a degree of 2 or 3, you can say it is irreducible if and only if f of x has a root. Root should exist in f. So first see the first condition. Let f of x is equal to ax plus b. We are going to consider with 1 degree polynomial, always we will be writing this ax plus b. We have already seen this. Where a is not equal to 0. So if a is equal to 0, what will happen? It will become a 0 polynomial in f of x. Suppose f of x is irreducible. So this is, when I say suppose f of x is irreducible, then there exists g of x, h of x belongs to f of x such that I can write it like this. So if I say a polynomial is reducible, automatically what does it mean? I can write that particular polynomial as a product of two other polynomials. So where the degree of this g of x and the degree of h of x should be less than this f of x. Is that clear? So where 1 is less than or equal to degree of g of x less than f of x. Able to understand this condition? So it's just mere arguments placed in the theorems. No need to worry about theorems, just plain arguments. So what did I tell you? Try to understand the concept clearly. A reducible polynomial is a polynomial which can be written as a product of two polynomials where with lower degree than of this particular polynomial. So automatically g and h degrees should be less than f. Automatically the f degree is 1. So that's why they are given like that. So 1 less than or equal to degree h of x less than h of x. So therefore f of x, in place of f of x, second substitute ax plus b is equal to g of x h of x. So taking degrees, operating the degrees on both sides. What is the degree of finding the degree of ax plus b? It's 1. Degree of g of x plus degree of h of x. We don't know what is the degree of that, but we can say it is less than f of x degree. So this is highly impossible. So this is less than 1 and this is less than 1. So 2 adding together, it should be equal to 1. So this is impossible since degree g of x plus h of x is greater than or equal to 2. Okay. So therefore f of x is irreducible over f. So we move on to the next condition. Next condition says that f of x belongs to capital F of x, be of degree 2 or 3. So what should be my conclusion? Then f will have a root or f is reducible. So suppose f of x is reducible over f, then f of x can be written as g of x into h of x. For g of x and h of x belongs to capital F of x, where the same condition what we have discussed earlier, 1 less than or equal to degree of g of x less than degree of f of x, and 1 less than or equal to degree of h of x less than degree f of x, because they are reducible polynomials. So therefore, since degree of f is equal to degree of g of x plus h of x and degree of f of x is equal to 2 or 3, we have degree of g of x plus degree of h of x is equal to 2 or 3. At least one of g of x and h of x has degree 1. Yes, no? Because when we say the sum of two degrees is equal to 2 or 3, 2 can be written as 1 plus 1. 3 can be written as 2 plus 1. Is that correct? So 3 cannot be written as 3 or 3. So at least one of g of x, h of x is degree 1 in both the cases. So what do I do? So let I consider g of x is 1. So g of x is ax plus b. A is not equal to 0. Now minus a inverse of b belongs to the field. You know that. So g of operating this in place of x minus a inverse of b is equal to, in place of x and substitute, minus a inverse of b. Okay, taking out this, multiplying this a inside. So you get a inverse will be the identity element. Identity element with b will be giving you b plus b. So minus b plus b will be giving you 0. So therefore a inverse of b is the root of g of x. Hence minus a inverse b is the root of f of x in f. So f has a root in f. Conversely, let f of x have a root, a belongs to f. So if f of x has a root, then I can say x minus a is a factor. If x minus a is a factor of f of x, by division algorithm, I can say the f of x which was factored can be written as the product of the factor into the divisor, where g of x belongs to capital F of x. This is by factor theorem. So where the remainder is 0 here. Okay. So hence f of x is reducible over capital F. Okay. So this is how the conclusion is. So a small brush up of the entire PPT. So we have started with what is reducibility, reducible problems to reducible problems, how to find the product of two polynomials as 0 and product of two polynomials to be non-zero, and then we discuss what is reducibility test. Reducibility test comes under two categories. Second one is let f of x and f of x be the degree 2 or 3, then you have a factor reducible over f, and the degree, if it is 1 necessarily, it is irreducible. This is what the reducibility test says. Okay, thanks for watching the video. Hope you understood. Let me catch up in your next videos. Thank you so much.